All right, welcome to 3-5 Summary of Curve Sketching. So this is where we put together all the different puzzle pieces that you've been learning over the last several weeks. So before we really dive into the curve sketching itself, we're going to do a little bit of just sort of review, summarizing a lot of the information that you've learned over the last few days. So first, here, just like I summarized at the end of yesterday's lesson, I've got these 4 different behaviors in terms of the shapes of the graph. So for this first one in blue, we've got increasing and concave down. In red, increasing and concave up. In green, I have decreasing and concave down. And in orange, I have decreasing and concave up. Now, remember, if we know that a function is increasing, then remember that means we know that f prime is positive. And if the graph is also concave downward, then that also means that we know that f double prime is negative. If we know that a function is increasing and concave up, then again, that means we know that f prime is positive and that f double prime is also positive. When we know that the graph is decreasing, again, that means f prime is negative, and concave down, that means f double prime is also negative. And finally, when we have decreasing and concave up, that means we know that f prime is negative and f double prime is positive. So remember, those are what we've studied basically between lesson 3.3 and 3.4. And so today we're really going to see how all of that information can come together and help us really form the shape of the graph, or basically to graph functions that are otherwise pretty unfamiliar to you. So to practice some of this information first, let's take a look at the following graph. Okay, so here on the left we have a given graph, and so we're going to use that graph to state the intervals or values where each of these descriptions occur. So first we're going to look for where f prime of x is greater than 0. So again, remember, if f prime is greater than 0, then that means we're saying that f prime is positive. And if we're saying that f prime is positive, then remember we're talking about where f is increasing. So we're just going to look at this graph of the function f and determine where is this function f increasing, where is it going up to the right. And if you look at this graph, let's see, on this first interval, notice that it's going down to the right, so that's decreasing. Here we are still decreasing, and then here we're still decreasing. So f prime of x is never positive for this particular function. So I'm just going to say NA or none. Okay, so now we're talking about the intervals where f prime of x is negative. And again, that means f is decreasing. And if f is decreasing, now we're talking about this first interval goes from negative infinity to negative 2. So negative infinity to negative 2. And then from negative 2 to 2. And finally from positive 2 to infinity. And remember, we do have to stop these intervals at negative 2, because remember that this function does have domain restrictions at negative 2 and positive 2, so we could never include those x values in any of our intervals, because the function does not exist at those values. All right, f double prime of x is greater than 0. In other words, f double prime is positive, and remember that would mean that f is concave up. So we need to look for something that's part of a bowl shape. Well, let's see, this first interval is definitely concave down. That's more like the top of an umbrella. From negative 2 to 0, though, so from negative 2 to 0, the function f is concave up. So we can say from negative 2 to 0. From 0 to 2, that's back to concave down. But then from 2 to infinity, we're back to concave up. So f double prime of x is positive on those intervals because f is concave up on those intervals. Now, whereas f double prime of x less than 0, so in other words, f double prime is negative, that means f is concave down. So f is concave down clearly from negative infinity to negative 2, so that first interval, as well as 0 to 2. Okay, now where is f prime of x equal to 0? Now remember, f prime of x equaling 0 means that we would have a horizontal tangent line there. Now it could mean that we have a relative maximum or relative minimum, but remember it doesn't have to be. It could be a situation where the function levels out but then continues going in the same direction, kind of like the 0, 0 of an x cubed graph. So I don't have that anywhere here though. It kind of flattens out here in the middle, but notice that that tangent line would still be at a slight angle downward. So even that's not a horizontal tangent line. So there are no locations, there are no values of x at which this function would have a horizontal tangent line. So f prime of x equals 0, this would be none. Or again, NA. And then finally, f double prime of x equals 0. Now remember, if f double prime of x equals 0, that's possibly where we would have a point of inflection. But remember, a point of inflection, not only would we need the second derivative to equal 0, but we would also need the concavity to change. But remember that the concavity does change at x equals 0. Remember, this function does change from concave up to concave down at x equals 0. So f double prime of x equals 0 at x equals 0. Just a reminder also that f prime of x could equal, or it could be undefined at a particular point, particularly if you have a vertical tangent line or if you have a corner point or cusp. So keep that in mind as well. Okay, so again, this is just to summarize how we can connect the behavior of the graph of a function, increasing, decreasing, concave up, concave down, how those all connect to the first derivative or the second derivative. So now that we've reviewed that, now let's actually talk about this summary of curve sketching. How can we put all of this calculus together to accurately graph a function that maybe you haven't never graphed before? All right, so here we go. So we're going to analyze and sketch the graph of each function. And the first one we're going to start with, this is a rational function right here. F of x equals 2x squared minus 18 over x squared minus 4. So in order to analyze and sketch, there are a lot of pieces of information that we're going to have to find, some of which are based on calculus, some of which are based on pre-calculus or previous courses. So first we're going to start with just the algebraic stuff, the non-calculus. So things like intercepts. So let's start by finding the domain, the range, the domain and the intercepts and any asymptotes. So starting with the domain. Now we know that the function will be undefined if the denominator is ever going to be 0, and the denominator will be 0 if x is plus or minus 2. So the domain would be x is not equal to plus or minus 2. Now for the intercepts. Now remember we have y-intercepts and x-intercepts. Let's start with the easier one, which is the y-intercept. And remember that y-intercepts we simply find by turning the x into a 0. So if I were to replace the x's here with a 0, then I'm going to have negative 18 over negative 4, which becomes positive 9/2. For my x-intercepts, or my roots, remember that that's going to be values of the function, the y, the output. That would make, that would be the x values that would make the output a 0. So that means we would need to set this function equal to 0. And that means we're going to set the numerator equal to 0. And if we do that, I'll just do this here on the side. If we do that, I have 2x squared minus 18 equals 0. If I factor out a 2, and factor the difference of squares. So we're going to get x equals plus or minus 3. So our x-intercepts, our roots, are going to be at 3, 0, and negative 3, 0. So those are going to be our intercepts. I'm going to erase this for space. If you need to see that again, go ahead and rewind. All right, now for vertical asymptotes, remember that vertical asymptotes we are going to find by looking for places that would make our denominator 0 in a rational function in particular. And so again, that was our domain restrictions here. X couldn't be plus or minus 2 because those would be values of x that would make our denominator 0. So that means this graph will have vertical asymptotes at x equals 2 and x equals negative 2. Those are the equations of the vertical asymptotes. And then if we have any horizontal asymptotes, let's find that. Now, remember way back in Unit 1, we used limits at infinity. We looked at the limit as x approaches positive infinity and the limit as x approaches negative infinity to look for horizontal asymptotes. But remember that that was really giving us justification for the shortcut that you had learned in pre-calculus. And because we're just trying to graph right now, we are not focusing on limits, we're focusing on the graphing. So if that's the case, I would encourage you to just use your shortcuts. Notice that the degree in the numerator matches the degree in the denominator. So remember that that means you will have a horizontal asymptote at the ratio of the leading coefficients. So that means this particular function does have a horizontal asymptote at y equals 2 over 1 or y equals 2. Okay, so that's where we're going to have our horizontal asymptote. So that's all of the sort of pre-calculus information that we could find. But now we need to start analyzing this function to determine on what interval or intervals does this function increase or decrease. Where does this function have a relative maximum or relative minimum, if at all? On what interval or intervals is this function concave up or concave down? And where, if any, does this function have a point of inflection? So at this point, now we're going to use all of the calculus to figure those things out. So that means I do need to find f prime of x, and then we're still going to need to find f double prime of x. And if you are looking ahead and thinking ahead, this is a rational function, which means to find f prime, you're going to need a quotient rule, or you can rewrite it as a product with a chain rule. But then you're also going to have to find the second derivative of that. So as you can probably guess, there's going to be some work ahead here. So the magic of recording, I am going to just make those magically appear. Okay, and magically there are the first and second derivatives for this particular function. If you need to sort of look at the work more closely, feel free to pause this video at this point, and you can take a look at the work before I move on. All right, so in finding those derivatives, remember the reason we do that is so we can find our critical numbers. So for f prime, if I were to set f prime equal to 0, then that would make the numerator equal to 0 when x equals 0. The denominator would equal 0 when x is plus or minus 2, but remember, those were already domain restrictions, so I don't need to worry about those. Similarly, for the second derivative, now, the second derivative will never equal 0. That numerator will never become a 0. 3x squared plus 4, that's always going to be positive. So this will never equal 0 in the numerator. The denominator is only going to equal 0 at plus or minus 2. And again, we already know that that's going to be a domain restriction. So the only critical number that we got for this entire first or second derivative was x equals 0. But remember, we do also have those domain restrictions at plus or minus 2. So now we're going to make the mother of all sign charts. The mother of all sign charts. And it's going to look like this. Okay, so I went ahead and just rewrote the function f prime and f double prime just to give us some space here. But remember, we're going to make our sign chart. Now, remember on your sign chart, On the number line, you would include any critical numbers and any domain restrictions. So remember, we had domain restrictions at plus or minus 2, and we had a critical number at 0. So that means we're going to need 3 lines here along our number line, which means we're really we're dividing our number line into 4 total intervals. So in order, we have -2, we have 0, and then we have +2. Now, like I said, this is the mother of all sign charts. Up until now, you've had 2 lines, one for f, and then one for either f prime or f double prime, whichever we were working with. But because we're looking at both, we're going to make this a 3-row sign chart. And the reason we did that, again, the bottom row is going to be for f, the middle row is for f prime, and the top row is for f double prime. Okay, now remember why -2 was in this chart. -2 was in this chart because it was a domain restriction for f, but it also made f prime and f double prime undefined. Now, 0 was in this chart because it made f prime 0. So on the f prime line, that's where I'm putting that 0. And then finally, 2 was in this chart for the same reason -2 is, which is it made f prime, and f double prime undefined. Okay, now, the reason that it was important for me to put the 0 for f prime, what this is saying is when I'm analyzing f prime's signs, positive or negative, I have 4 distinct intervals that I have to investigate. -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. Notice for f double prime, even though I have this line right here, that line was only there because 0 needed to be in our chart. But really, for f double prime, the only intervals I'm looking at are -infinity to -2, -2 to 2. There's nothing interrupting f double prime at 0. So this whole thing right here is considered one interval for f double prime. And then finally we have from 2 to infinity. So just kind of keep that in mind as we go through this. Okay, so now we're going to go ahead and do the same thing you've been doing, which is we're going to pick just some test values. So from -infinity to -2, we can choose, say, -3. Now, in f prime, so here's f prime, notice in f prime, that denominator is getting squared, which means that denominator is always going to be positive. Always, always, always. So the only thing, and then 20, of course, is always positive. So the only thing we have to figure out is what's going to happen with x. So if x is -3, I've got a positive times a negative divided by a positive, and that's going to be a negative. Now remember, this was analyzing f prime. So on the f prime line, that's going to be a negative. Again, be careful not to put it into the wrong line. If I substitute it into f prime, I better write that on f prime. For f double prime, now again in that numerator, -20 is always negative. 3x squared plus 4 is always positive. And so what that means is for f double prime, that numerator is always going to have a result of being negative, and I just have to figure out what's happening in the denominator. So if x is -3, then -3 squared is 9. 9 minus 4 is positive. A positive cubed is still positive. So this is going to make f double prime negative. All right, between -2 and 0, of course, we can try -1. So if x is -1, then that means in f prime, we're going to have a positive times a negative divided by a positive, which is going to be a negative. Sorry, I just did exactly what I told you not to do. This was for f prime. That's going to be a negative for f prime. All right, but in f double prime, again, if I use -1, that's going to be -1 squared, which is 1. 1 minus 4 is a negative. A negative cubed will be negative, which means that result for f double prime is going to be positive. But remember how I told you that f double prime is only one interval from -2 to 2? then that means if this was positive here, then this is still positive from 0 to 2, because remember, this is still one interval. And then from 0 to 2, we can use x equals positive 1. Well, that means then in f prime, we have a positive times a positive divided by a positive, which of course is positive. And then finally, greater than 2, we can use x equals 3. So for f prime, that's going to be a positive times a positive divided by a positive. That is all positive. And then for f double prime, again, the numerator is always going to be a negative. But if I put in a 3 for x, I'm going to have a positive, which means f double prime will be negative. Okay, so now we get to go back and think about what we did at the very beginning of the lesson when I showed you those 4 different shapes of graphs and what they meant in terms of increasing, decreasing, concave up, concave down. So in this first interval from negative infinity to negative 2, f prime is negative, which means I know that my graph should be decreasing. And f double prime is also negative, which means my graph should be concave downward. So from negative infinity to negative 2, for f, I'm going to just draw that shape. Again, it's decreasing and concave down, and that's the shape that our graph should have. From negative 2 to 0, f prime is negative, so again, we should be decreasing. But f double prime is positive, so that means this needs to bend concave up. From 0 to 2, f prime is now positive, meaning our function should now be increasing. F double prime is still positive, which means this now bends concave upward. And finally, from 2 to infinity, f prime is positive, so again, that means f is increasing. F double prime is negative, which means this is now concave downward. So we have this shape on that last interval. So what that means then is we should expect our graph to have a shape that looks something like this, and then this, and then this, and then this. But remember, we also had all of that other information we found earlier, such as the intercepts and the asymptotes. So between that information and what we came up with right here on our sign chart, we're now going to be able to sketch this graph. Okay, so I've now filled in, or just written down, all of the information from our previous screen that has our intercepts and our asymptotes, and here's our blank grid. So the first thing I want to do is actually I want to put in the asymptotes, because what that's going to do is sort of establish the framework for the rest of our graph. So we've got vertical asymptotes at plus or minus 2, x equals plus or minus 2. So I'm going to put in my vertical asymptotes there. And there. And at y equals positive 2, which is right here. Okay, so again, the asymptotes are really good for us because they sort of provide the general framework, a skeleton that our graph has to work around. And again, notice how that really helps us divide up those different intervals. We have negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. We also have intercepts. Remember, we also have intercepts. 0 comma 9 halves. Remember, 9 halves is 4 1/2. So 0 comma 4 1/2. There is our y-intercept right there. So we know that our graph is going to have to go through that point. We also have x-intercepts at plus or minus 3. So that means right here and right here. So that also means our graph has to go through those points. Now, here's where we have sort of the puzzle pieces. We know that from negative infinity to negative 2, our graph has to have this shape here. It has to have sort of this downward, decreasing, concave downward shape. So I need to take that shape and move it into this graph. Well, remember, a horizontal asymptote does tell us what has to eventually happen on the far ends of the graph, which means I have to either start right above it or right below it. But if I'm having to decrease, that means I'm going to start below it, and we have to do something, oops, that's very messy, something like that. Again, we need that general shape that we had here, but it does have to go through our x-intercept. I kind of missed, but you get the idea. Now, from -2 to 0, remember we have to have this shape. We have to be decreasing and concave up. Now remember, at a vertical asymptote, you have one of two places to begin. You either have to begin all the way at the bottom and come up, or you have to start all the way at the top and come down. Because we know it has to be this shape, we have no choice but to start at the top and to come all the way down until we hit the y-intercept at 0, 4.5. Now from 0 to 2, now we've got this increasing and concave up shape. And remember, I do have to start where I left off because there's no discontinuity there. So I'm starting here at this y-intercept, and again, that means I'm going to have to increase and be concave up as we get closer to that vertical asymptote. So again, that means we have to increase forever. And finally, we have our last interval from 2 to infinity. We have to have this shape here increasing and concave down. So again, either I have to start at the top or I have to start at the bottom. But if I'm increasing, I have no choice but to start at the bottom. But remember, I also have to go through this root, this x-intercept, and then I do have to flatten out at this horizontal asymptote. So it's going to look something like that. And again, I kind of missed, but you get the idea. I'll just make that point a little bit bigger and no one will notice the difference. And that right there is our graph of this particular rational function. Notice it has all of the behaviors that we needed. Now, there's two things that we haven't found yet that we will be asked to find. Does this function have any relative extrema? Well, remember, relative extrema, we are looking for places where f prime changes signs. And in this case, we have f prime going from negative to positive at x equals 0. So remember, if f prime changes from negative to positive, then that means we have a relative minimum. So we do have a relative minimum at x equals 0, and the y-coordinate for that we already know is 9/2. There is no relative maximum. Because there is no place where f prime is changing from positive to negative, where the function is defined, especially. And then also any points of inflection. Remember, points of inflection, we're looking for places where the concavity changes, but there is a point. Now, the concavity does change at -2, but remember, at -2 we have a vertical asymptote. There is no point there, so you can't have a point of inflection. Similarly, at x equals +2, f double prime does change signs at +2, so concavity does change, but there is no actual point there. There's a vertical asymptote, so you can't have a point of inflection there either. So in this case, there was no points of inflection either. All right. That is a lot of stuff, but that's what we're trying to do here with this summary of curve sketching. Let's go through one more example, but it's going to go a lot more quickly this time. All right, so this time we're going to use f of x equals x squared minus x all over x plus 1 quantity squared. So once again, first thing we're going to do is we're going to find the domain. And this function will be undefined when x is -1. So x cannot equal -1 for the domain. Now, for the intercepts, in the previous example, I specifically made a difference or distinguished between the y-intercept and the x-intercept. It doesn't really matter. You should know which one's which. But remember, we're finding these just so we can make the graph. So for the x-intercept, for the y-intercept, when I make the x a 0, that is going to be 0 over 1, so that's going to be 0, 0. But for the for the x-intercepts, If I make that numerator equal to 0, that means I'm going to have x squared minus x equals 0, which is x times x minus 1 equals 0. So that means x equals 0 or x equals 1. Well, we already have the 0. That was also our y-intercept. But we also have when x is 1. Okay, now for vertical asymptote, remember this is going to be undefined when x is negative 1, so the vertical asymptote is at x equals negative 1. For the horizontal asymptote, now remember, to use the shortcut for rational functions, you have to imagine that the function is multiplied out. You need it to be in the form ax to the m plus bx to the m minus 1 dot dot dot. Oh, I don't want to use a b. But you get the idea. It needs to be multiplied out. Now notice that the denominator here is not multiplied out. It's in factored form. So you at least need to imagine what will it look like? What is it going to lead with if you were to multiply this out? If you had x plus 1 times x plus 1, what is the first term going to be? And it's going to be an x squared. So that means for the horizontal asymptote, the degree of the numerator matches the degree of the denominator, and the leading coefficients are both a 1, so your horizontal asymptote will be at y equals 1. All right. And once again, through the magic of recording video, let's make the first and the second derivative magically appear here. And there are the first and second derivatives. Okay, so as usual, we're going to look first for critical numbers from the first derivative. So if I were to set that first derivative equal to 0, then that's going to happen when 3x minus 1 equals 0, so x is going to equal 1/3. And yes, we are going to need to figure out the y-coordinate for that. The denominator will equal 0 when x is negative 1, but remember, we already know that that's going to be a domain restriction. In f double prime, our numerator will be 0 when x is 1. Fortunately, we've already figured out that y-coordinate because remember that's actually one of our intercepts. And the denominator is going to be 0 again at x equals negative 1, which is a domain restriction. Okay. While we're here, let's go ahead and figure out this y-coordinate now for when x is 1/3. So when x is 1/3, f of 1/3, remember we're going to the original function now, that's going to be 1/3 squared minus 1/3 all over 1/3 plus 1 squared. Now that's going to be 1/9 minus 1/3 over, this is going to be a 4/3 squared, which is 16/9. 1/9 minus 3/9, so that's going to be negative 2/9 over 16/9. And remember, that's the same as multiplying negative 2/9 times 9/16, and we finally get negative 1/8. So this is going to be at the point 1/3 comma negative 1/8. All right, so now we've got all of the information that we need. Remember, we've got critical number at x equals 1/3 and x equals 1. We have domain restrictions at x equals negative 1. So let's put all of that information into our sign chart. All right, so here is our sign chart all set up. And here are the other pieces of information that we already know, and I've already got my grid all set up. And you'll notice that my scale, I've already determined that for my x-axis, I'm actually going to go by 1/3. And the reason I chose to do that is because I knew that one of my critical numbers was at x equals 1/3. So it would seem to make sense that I might try dividing my x-axis into 1/3 units. And then similarly for my y-axis, notice that I'm going by 1/4, and that's because I do need to include x equals 1, but remember that the y-coordinate of when x is 1/3 turned out to be negative 1/8. So I wanted to make sure that this was divided up small enough that I could still figure out around where negative 1/8 should be. So that's going to be halfway down between 0 and negative 1/4. Okay, so going back to our sign chart here, remember negative 1 is in this chart because that is a domain restriction. It makes f, f prime, and f double prime undefined all the way up. 1/3 was in our chart because it made f prime 0. And 1 was in our chart because it made f double prime 0. All right, so now, again, going back and analyzing here a little bit, notice for f prime, that denominator could be positive or negative. That numerator can be positive or negative, so we are going to have to investigate both of those to figure out our signs. For f double prime, that denominator is going to always be positive. And negative 6, of course, is always going to be negative. So for f double prime, all we're going to really have to focus in on then is what happens with x minus 1, because then I'm going to have a negative times that divided by a positive. Okay, so let's go ahead and get to it. So less than negative 1, so maybe when x is negative 2. So if I put in a negative 2 for f prime, my numerator will be a negative. And my denominator will be a negative 2 plus 1 is negative 1 cubed, which will be negative as well. So f prime is going to be a negative divided by a negative, which is positive. F double prime, when x is negative 2, again, negative 2 minus 1 will be a negative. So now I've got a negative times a negative, which is positive, divided by a positive, which will be positive. Between negative 1 and 1/3, 0 seems like a nice choice there. So if I use x equals 0 for f prime, then in the numerator, I'm going to have 0 minus 1, which is negative. In the denominator, I'm going to have 0 plus 1, which is 1, cubed, which is positive. So now I've got a negative divided by a positive, which is negative. For f double prime, if I put in a 0 for x, then that means I'm going to have 0 minus 1, which is negative, times another negative, which is positive, divided by a positive, which is positive. Now remember, for f double prime, there isn't actually a stopping point at 1/3. The 1/3 was for f prime. So for f double prime, I know that this third interval is still going to be positive. It hasn't had a chance to change. But for f prime, now between 1/3 and 1, we have no choice but to use something like 2/3. But that's not so bad, because when you look at f prime, 3 times 2/3 is just going to be 2. And then 2 minus 1 is going to be positive. And then 2/3 plus 1 will be a positive cubed, which is still positive. So we do get a positive there. And finally, greater than 1, so maybe when x is 2. In the numerator of f prime, we're going to get a positive. Denominator will be positive. So this is still going to be positive. And that should make sense because, again, f prime also didn't have a stopping point at 1. Remember, the 1 is only in here because of f double prime. And then when x is 2, f double prime will be a negative times a positive, which is negative, divided by a positive, which is negative. Okay, so now we can get the shapes here. F prime is positive, so we are increasing. F double prime is positive, we are concave up. So increasing and concave up is going to look like that. Now for negative 1 to 1/3, we are f prime is negative, decreasing, and concave up. So it's going to look something like that. And then x from 1/3 to 1, we are increasing and concave up. And finally, for this last interval, we are increasing, f prime is positive, and concave down. So again, we've got something like this, and then something like this, and then this, and then this. So our graph should have something of this kind of a shape. So remember, we're going to start by putting in our asymptotes, because that's going to give us a little bit of a skeleton for this graph. So the asymptotes, remember, are x equals negative 1. And then our horizontal asymptote is at y equals positive 1. And then remember, we had our intercepts at 0, 0, and at 1, 0. And remember, we did have this point here at x equals 1/3. And notice, at x equals 1/3, the derivative is 0, and f prime changes from negative to positive. So we do have a relative minimum at 1/3, negative 1/8. So I actually want to plot that point. So remember, 1/3, negative 1/8, That's going to be right here. So my graph does have to go through this x-intercept, and it has to hit that relative minimum before it starts to go upward again. All right, so now, in terms of points of inflection, by the way, we do have a point of inflection also, remember? That is where the second derivative was 0, and the second derivative changes signs. So we do have a point of inflection at 1, 0, which remember is already in our graph because it was one of our intercepts. Let me change that to a blue point, so the whole graph is one color. Okay, so now, remember the first interval, negative infinity to negative 1, we have to be increasing and concave up. Well, if I have to end at this vertical asymptote, that means I'm going to have to be up here. I can't start down here because remember that horizontal asymptote is telling me that eventually on the far left side, my graph has to be riding right along it. So I can't start down here because that means I'm ignoring what the horizontal asymptote is telling me. And I can't start underneath because, again, the way that the horizontal asymptote behaves, we have to end up either just being right above it or right below it. And I'll talk more about that at the very end of the lesson here. All right, from negative 1 to 1/3, again, that's this point here, we are decreasing and concave up. So something, oops, that is very messy, so something like that. And then from 1/3 to 1, something, it's going to be very, very tricky, just because it's so flat, but we still have to make it this shape here. And then finally, from 1 to infinity. Now, remember, we need this shape here from this point, so it has to be that. And that is the sketch of the graph of our function. All right, yeah, I kind of messed up from negative 1 to 1/3. That's not the best shape there, but you get the idea. Okay, now I do want to talk a little bit more, just to wrap up here, I want to talk a little bit more about the horizontal asymptote behavior. So at a horizontal asymptote, your graph can do, let's say we're just going on the positive infinity side, your graph can do one of three things. Your graph could flatten out this way, or your graph might dip below and then come back, or your graph might actually oscillate and then sort of flatten out but still oscillate. So those are some of the different things that can happen. Now, how do we know which one it's going to do based on our sign chart? Well, if you look at the blue one is only decreasing and concave up the entire time. That's one behavior. But on the red one, this is actually decreasing and concave up until this point, and then increasing and concave up until about there, and then increasing and concave down. In order to get this red shape, you would actually have to have 3 separate intervals show up in your sign chart to describe that end behavior. Again, that's as opposed to the blue shape, which is just one consistent interval. It is decreasing and concave up that whole time. And how would you know if you had the green one? Well, you would have an infinite number of intervals. So clearly, I'm not going to give you that because that might take a little longer. Okay, so again, this is the summary of curve sketching. It's taking everything you've learned and really throwing it all together. All right, good luck, everyone.